bit early and start talking a little bit about some like prerequisite stuff. So my name's Aiden. Um, I'm a fourth year math undergrad going into my PhD next year. I study math. I love learning math. I love teaching math. So mathematics is kind of my life, and math education is, I would say, my secondary passion. This is my first time teaching kind of course to a large number of people, but I have done a lot of tutoring and a lot of one-on-one help. I'm really excited to be presenting today. As for like course stuff, this course doesn't have homework, or not, things won't be graded, but we will try and give you some exercises that we strongly encourage you to do. The main way you learn math is by doing math, and the main way you do math, at least at this level, is you get problems from people who've done the math and do the problems. I'll try not to give any problems that are just busy work. Any problem I give you is a problem that I think solving is really valuable. We're also going to... The structure of the course is such that if you don't get something when I present it, Ethan is going to present on code, basically implementing all the things we're going to be talking about in Lua. And it's set up so that kind of the same things will be talked about twice. Once by Ethan, once by myself. So I wouldn't, like, if you feel like you don't quite get it on the first pass, there's a security advisor in the background, then I wouldn't worry about it too much, because you'll probably understand on the second pass. What else? So this is the 10-week course. It's going to be a little bit weird if you've never done anything. If you've ever seen like a college level linear algebra course, then this kind of our planned schedule is a little bit odd. Because we're focusing on things that we think people will actually use, especially in Roblox. So we're going to devote a pretty substantial amount of time to talking about this, actually, affine algebra, which is kind of the next level up of linear algebra, and is actually the kind of stuff you're doing whenever you're working with vectors in three-dimensional spaces. So with that, I guess, Ethan, do you have anything that I missed?
Nothing immediately comes to mind, but I'll mention it on Thursday if I do think of something.
Okay. And you're recording, right?
Yep, it's going.
Perfect. So with that, we'll start talking about vectors, products, and norms. Again, if you have any, please, I guess one custodial thing, please mute, and if you have questions, you can like wave to me in the voice chat, so the chat associated with this, the voice chat we're all in, or just ask the question in there, and I'll try and answer it if I think it's relevant to the class, or if you raise your hand, you can unmute and ask questions. And with that, we'll start. So this is lecture 1, and we're going to talk about vectors, products, and norms. But before we get to that, we have to go over some kind of basic ways that we talk about math, and this is going to be lists and sets. So what is a list? Mathematicians, when there's something important to us, we like to give it a name, and when we give something a name, we like to tell you what that name means. A lot of times math is accused of being kind of impenetrable because it has a lot of jargon, a lot of words that people may not have heard before, and that's very true. That's a legitimate criticism of mathematics, but I also think that there's a reason we have all these words, and it's because it gets very tiring to talk about math without well-defined concepts. So for us, like a list is going to be some data with order. So when you write things down in a list, you write them one after the other. You could have a list of numbers, 1, 2, 3, 4, 5. You get a list of things, apples, oranges, pears, or lists of symbols, like A, B, and C. If I want to write a list that's quite long, like if I want to write something that's 1,000,000 numbers long, I really can't do that. So I have to abbreviate that some way. And when we want to do that, we use the ellipses, the dot dot dot. And if it's ever unclear what the dot 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 should be filling in, then that's not a failure on your part. That's a failure on my part. So I'll only try and use ellipses when it's very clear what the interim things should be. So for instance, when I write 1, 2, dot 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 1,000,000, I mean 1, 2, 3, 4, 5, 6, on and on and on until you get to 1,000,000. Similarly, if I'm writing with letters, then letters are ordered. We have an alphabetical order on them. We can write A through Z by writing A, B, dot 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 Z, and that's to be interpreted as like the letters between A and Z. Again, it's kind of my fault if writing the ellipses fails to help you, or fails to be communicated well. For sets, we talked about lists being data with an order. Sometimes we really only care about data without an order. We don't care about the order that the data is presented in which case we have to have some sort of different notation. So the list 1, 2, 3, for instance, is different from the list 3, 2, 1 because they have a different order. But they have the same numbers in that list. And when I want to write this down, I'm going to put these squiggly braces around the numbers or whatever thing I'm putting in the set. So yeah, like while the list 1, 2, 3 and the list 3, 2, 1 aren't equal, the set 1, 2, 3 and the set 3, 2, 1 are equal. And again, this is just basically to make it easier to talk about things. A lot of things we talk about will be sets, and that's not going to be super important. But I just want you to know that when I say a set, I mean just like a collection of things that are kind of grouped together, and we don't really care about the ordering on them. Now, in order to keep it clean when I talk about lists, I'm going to put parentheses around them. So if I ever write a list, I'll put parentheses around them. If I ever write a set, I'll put the squiggly braces around them. And this is because, like, if I write the list 1, 2, 3 in the middle of a sentence, and I don't put the parentheses around them, then it's hard to differentiate them from the rest of the sentence. We also don't actually care about duplicate data in sets. So if we have like multiple copies of the same thing in one set, then they're equal. So the set 1, 1 is actually equal to the set just 1. But that won't come up that much. Now, importantly, all the examples of sets that I've given are finite collections of things. So there are some finite number of them, but there are infinite sets. So there are sets of, for instance, the integers, all the numbers, 0, 1, 2, -1, -2. This is an infinitely big set. If you try to figure out how many elements there are, you'll never be able to succeed. And so actually most of the sets we're going to talk about today are infinite, but we're not going to really talk about how to write them down or how to do stuff like that. There was a question. Do you want to ask it in chat, or do you want to ask it in voice?
All right. On the slide, it said that sets cannot have duplicate data. It says a set is data without an order or without duplicates. However, you then stated that sets don't care if there's duplicates, and that sort of conflicts, from my understanding.
Sure.
If you could clarify on that.
One way to think about it is, like when you in code you have like constructors, right? So you have like a way of like, or in Lua you usually do like .new. You can essentially, like, in the .new for sets, when you're defining a set, you can put in duplicate data, but the set itself will not store it, quote unquote. So, when I say that it can't have duplicate data, what I really mean is that a set with duplicate data and without duplicate data are in fact identical as sets. So yeah, from a coding perspective, I would think about it as like a constructor thing. You can pass in a list of all ones, and then we'll return a set of just one.
Okay, thank you.
Cool. So yeah. Again, mathematicians like to give things names. We like to give things symbols, and we do this to be abundantly clear. So for instance, we're going to let this weird-looking R thing denote the real numbers. And the real numbers are the numbers that you've used your whole life. So, all the numbers that you would use to count, like 1, 2, 3, 4, 5, 6, on and on, those are all real numbers. Fractions are real numbers. Decimals are real numbers. Irrational numbers are real numbers. Basically, everything you've ever worked with, except maybe complex numbers, are real numbers. So we're going to use this R symbol to denote that. Now, why do we use this weird R? Well, we use it because if I used a normal looking R, it would be more confusing. So, again, mathematicians, we want to make things as unconfusing as possible, and so paradoxically, we throw a lot of weird symbols at you. But it's kind of this catch-22 where if you don't use the weird symbol, then it isn't clear necessarily what it means. So like every floating point number or you've ever used is a real number, for instance, to tie it back to Lua. That is a good question, Nezua. I'm not sure if I'm saying your name right. Sets. There's a difference between an order and an ordering is kind of the short answer, and that's a terrible answer. But the question was basically, my slide said that sets aren't ordered, but things like the integers are assumed to be ordered because you can say that like 0 is less than 1. And this is a kind of nuanced point, but we don't have time for that. So we can talk about that some other time, probably in a different chat. We're going to write lists of real numbers quite often. And I'm basically always going to use this notation, where x is equal to this list of real numbers, x1, x2, up through xn. Now again, this ... means we're going x1, x2, x3, x4, x5, on and on and on, until we get to some number n. And n is going to be the size of this vector. Now again, these lists are ordered, so the list 1, 2 is different from the list 2, 1. That's very important. Weird R is a set. Yeah. So now, again, we like to give names to things. So if we want to talk about the set of all possible lists of real numbers, we're going to call it Rn. And so the n here stands for the number of numbers in our list, and the R stands for the fact that we're using the real numbers. A concrete example of this is you've all probably worked with vector3s, or at least heard about them. And so R3 is basically the list of vector3s. That's one way to think about it. So right, because what is a vector3? It's a list of 3 numbers. And so R3 is the set of all possible lists of 3 numbers. Now, I have some asides in here because they're important. A lot of people get bogged down. A lot of people get confused when I write something like x subscript 1. And I think the confusion comes down to this assumption that x sub 1 and x must be related. But let's imagine you're coding, and you have a variable called x1, like as a string here, and a variable called x. If they're different variables, you can't, without looking at the code, figure out whether or not x1 and x are related. Similarly, mathematicians, we don't want to write out the full word 1. So we're just going to do a subscript 1, but it's basically the same thing. It's a completely different variable. And without looking at the surrounding context, you cannot tell whether x and x1 are related. Now, that is annoying, especially to new mathematicians. So I am always going to use the notation that, for instance, x sub 1 is the first element in the list of real numbers x. And that's not necessarily always going to be used. That's very commonly used, and it's very commonly assumed it's that. But just for the purposes of this class, to make everything run smoothly, I'm going to use this x sub 1, x sub 2, x sub 3 always. And if I write x sub I, so maybe x sub a million, that's going to be the millionth item in the list x. I hope that makes sense. Are there any questions about that? About like what x sub 1 means? Sure. You want to hop in chat again?
Yeah. So when you see x equals and then like a set and it's x of 1, x of 2, x of 3.
I don't know a set, that is a list.
Sorry, a list.
All good.
So the relationship between x of 1 and x is that x of 1 is like a sub index of x essentially.
So right, imagine that so x is like the name I've given to the whole list. And x sub 1 is the first item on that list. So whenever I talk about a list, you can think about writing out a list with a pen and paper, right? You would write like 1 and then some item, and then 2 and then some item, then 3 and then some item. So the x sub 1 is just the name we've given to that first item. X sub 2 is the name we've given to the second item. Does that make sense? So actually, I think I'm not actually a Roblox programmer, but I think in Roblox Vector3s, x sub 1 would actually be like vector3.x, I believe. Or at least that's true in the coordinate system. Like your first coordinate is x, your second coordinate is y. Mathematicians, we don't like to use up variable names. So we're just going to use x over and over again if we can, instead of using x, y, and z, if that makes sense. Yeah. Does that clear it up?
Yeah, so it's basically like a sub-index, if I'm understanding this correctly.
Sure. But I would honestly just think of x1 as a number. It's just a number that happens to be the first element of the list x.
It's a bit confusing.
That might be a distinction without a difference.
About it later.
Yeah. Sounds good. So I like the questions though. Questions are good. Yeah, so Borbs said it well, which is that like x1 is the label we've given to the first number in the list. But right, like if in Lua I say x1 equals 2, then like x1 is the label we've given to the number 2. But if you ask Lua to print x1, it'll also print 2, right? It's not going to print the string x1. Yeah. So there's going to be an overarching theme in this, which is that mathematicians like to give things names. And the name we've come up with for Rn, yes, that is correct. The code snippet is correct. Sorry. The name we've given to Rn, which is the set, is Euclidean space. So the definition of n-dimensional Euclidean space is the set of all. It basically is Rn. Those are those are words for the same thing. And you've probably heard this referred to as like 3D space. So 3D space is really R3. It's the set of all points in three-dimensional Euclidean space. I might call it ND, or 4D, a million D space. Or if the size of the space doesn't matter, if the dimension doesn't really matter, I'll just refer to it as Euclidean space. So if I say Euclidean space, I just mean some set of lists of real numbers. And we're going to call the points in Euclidean space, we're going to call the elements of that set vectors. So this is kind of a very important definition because I've just stated perhaps the most hotly contested definition in lower division. So that's mathematics, which is the definition of a vector. And the definition I've given you is that a vector is a list of some number of real numbers. The question was asked in chat whether four-dimensional space is considered non-Euclidean, and the answer is no. Four-dimensional space is Euclidean. You could have billion-dimensional space that's Euclidean. That might seem strange, but we'll get to that, which is right here. The most common question I'm asked when I talk about higher dimensional spaces is, why do we care about them? And physicists have an answer, and I don't like the physics answer, particularly because I am a mathematician. In my opinion, the best way to think about higher dimensional Euclidean space is not as anything physical. It's just as a way of keeping track of lists of numbers. So, an analogy I'm going to come back to a bunch is, let's say that I'm trying to keep track, I'm a bank, or I'm running a Roblox bank maybe. I'm trying to keep track of how much money all of my clients have. Let's say there are 1 million people who use my bank. And I'm trying to keep track of how much money each of them has. I have to keep track of 1 million numbers, right? Now, ideally, what I would do is I would give every user of my bank a unique number. And that number would correspond to a bank account. And so, maybe the first customer gets bank account 1, the second customer gets bank account 2, right? On and on, up to all the way to 1 million users, right? So now I've written down a list of 1 million values, right? And I've just said that a vector is just a list of real numbers. So basically, I'm using a million-dimensional vector, right? So, I am using this million-dimensional Euclidean space, but thinking about it as some sort of like physical thing, trying to imagine the properties of million-dimensional physical space, you don't really need to get into it at all. You can really just think about keeping track of lists of numbers. And so this is, in my opinion, the better way of thinking about higher dimensional space, at least until you get a better intuition for these kinds of spaces. Now, the chat is very interesting, and I like the discussion. However, it is difficult for me to tell what actual questions are. So if you guys could talk about the lecture in the chat, like the V101 chat, and keep questions to the lecture, that would be better. Because I can't really tell if people are asking questions. All right. Now, I like this bank analogy. I like it a lot. So let's run with it. Let's say I am a poor, tired intern that a bank has hired. And they want me to go, they've decided to give everyone $1 for some reason. Maybe it was a promotion. And so they've hired me as an intern to go through every single account and give every single person $1. This is terrible, right? I don't want to have to go through and ask ask the computer to add $1 to every account, right? So I really want a way to do this all at once. I want to say just like tell the computer in one command, add $1 to every single person's account. Well, how would I do that? You can, well, the kind of simple answer is you can think about, I'm adding $1 to each person's account. So really, I have a list of additions, right? So I'm adding $1 to the first person's account. I'm adding $1 to the second person's account, on and on and on. And I'm going to add $1 to everyone's account. So I have a list of 1,000,000 plus ones. And well, we've been talking about lists of numbers being vectors. So I could store that list of ones as a vector, a 1,000,000-dimensional vector. And then it would be really nice if I could just add those two vectors together, meaning that I just basically add $1 to everyone's account all at once. And you could do this with any amount of dollars. If I want to give, some people more money and some people less money, then I could store the list of exactly which user gets what amount of money and in a vector, and then add that up. Similarly, if I want to do interest, if I want to give everyone 1% interest, I'd have to go through and multiply every number by 1.01. So it'd be really nice if we could just write down a way to multiply all the values in the vector all at once by some number. And we can do this because we're mathematicians. The beautiful thing about math is if you want to define some operation, we just can do it. So it turns out we can actually add, subtract, and even kind of multiply vectors. The addition and subtraction are pretty easy. If I have two vectors that have the same number of entries, so they're basically the same size, then I can add them by just adding each of their components. So a good example of this is if I have like a vector 3, if I have a three-dimensional vector that's 1, 0, 3, and I add it to 0, 2, 0, then the resulting vector, the vector addition, would give me 1, 2, 3. I could also subtract similarly. Now this is really important. This solves our problem. Where if I'm the poor tired intern now, I can just have the computer make a vector of 1,000,000 ones, and I can add that vector to my original vector, and boom, I've given every single person in the bank $1. And this is what it looks like. If I have the vector 1, 1, and I add the vector 1, 3, then I'm going to get the vector 2, 4. So you can see that the kind of resulting point up on the upper right, if you go down to the x-axis, it has a value of 2. If you go to the y-axis, it has a value of 4. So this is the vector 2, 4. And it's the way you get 2, 4 is you add 1 and 1, you get 2. You add 1 and 3, you get 4. Now the multiplication gets a little bit more funky. Right now, we're really only going to talk about scaling vectors. So what does it mean to scale a vector? Well, again, like in my banking analogy, if I want to give everyone 1% interest, then I would want to multiply every single bank account by 1.01. And to write this down, we're going to write down that if you multiply a real number in a vector, you just multiply that real number times every entry of the vector. Now, I'm guessing a lot of you are wondering about this weird curly A looking thing. That is the Greek letter alpha. I use the Greek letter alpha because I want it to look as different as possible from x, right? So in this case, alpha is some. Oh, yes, I did leave in the weird E looking thing. And that is my fault. I did not catch that. I was trying to avoid using that. So this is basically just a shorthand way that mathematicians use to say that something is in a set. So the statement alpha, to this squiggly looking A thing, And then the weird E thing, and then R means that alpha is in the set of real numbers. And I'm very sorry for leaving that in. I meant to not introduce that. That's my bad. But it just means in. And the reason it looks like an E is because it's actually read like in or element of. And it's very useful. Mathematicians use it all the time because it's very tedious to write element of all the time. And it's actually also tedious to put words in the middle of math equations. So that's why we use this like E thing. And then like X being in Rn, so the X element sign Rn, that means that X is a vector, is all I'm saying. And so we call this scalar multiplication because we're scaling our vector by some number, right? Because like scaling means to change the size of it. So if I scale something by 2, I'm making it twice as long, or I'm making it twice as big because we're scaling it up by 2. And so this is what we do in the example. We have like 2 times 1 comma 1 is equal. Oh, I'm cutting out. What am I okay? I'll assume I'm okay. Cool. So if you see, we can scale this vector 1 comma 1 by 2, and we get 2 comma 2. And because of this, we sometimes call the numbers in R scalars, because they are the things that scale vectors. And so you can see an example of scaling a vector here. If we scale 1 comma 1 by 2, we get 2 comma 2, which if you look at the X, we have 2. If you look at the Y, we have 2. So this point in the upper right is 2 comma 2. Yeah, so that's scalar multiplication. Are there any questions about scalar multiplication? It can be a little bit weird to say that we can multiply like a number in a list. Notation. I wrote it down, but I wasn't super clear. So you write it down just like you'd write down any form of multiplication, which is just you write down the 2 variables next to each other. If it's not clear, you can put the little dot for multiply. The one thing you absolutely cannot do is use an X. If you use the X times symbol, there will be riots in the street. The world will come to an end, and mathematicians everywhere will cry themselves to sleep at night. But you can use basically anything else you want. And the reason that mathematicians do this is because, for a similar reason why we give things distinct names, when things are kind of the same, right? When things are very similar, we like to give them similar names and similar notations, because really you can think about scalar multiplication as being very similar to every other kind of multiplication you've ever done. And so the reason we write it similarly is because they really are quite similar. Brad has already pointed out an interesting problem, which we'll get to. Now, again, on the theme, mathematicians like to give things names. There's a very important vector that we haven't really talked about yet, which is the vector of all zeros. Now, to get there, we're going to go on a little bit of a trip. So I've talked about scalar multiplication, and that means that I can multiply a vector, I can multiply a list of real numbers, by -1. And what that will do is it will take every real number in the list, and it will replace it with its negative. So, right, like the multiplying the vector 1 comma 1 by -1 would give you the vector -1 comma -1. We call this the negation of a vector x, and we write it as -x, right? So this should be familiar to you. If you've ever worked with positive numbers, you've probably also worked with negative numbers. And the way we write negative numbers is we put a minus sign before them. And if I add 1 and -1, it's the same thing as subtracting 1 from 1, as you can see here. And this is true for the negation of a vector as well. If I add x and its negation, it's the same thing as subtracting x from itself. This is basically like a command to say, remove all the money in everyone's account, right? How would I do that? Well, I would subtract the amount of money they currently have from the amount from their account. That would leave them with 0. So you can see that if we subtract x and x, we get the vector of all zeros. This vector has a name, and we call it the 0 vector. It's also sometimes called the origin. It's sometimes called the origin, but that's usually only, well, that's more often in 3 dimensions and less often in higher dimensions. So we're going to call it the 0 vector most of the time. Now, this kind of example, it doesn't matter that much, but if you subtract a real number from a real number, if you subtract 2 numbers and you get 0, then those 2 numbers must be equal. So there was a question about scalars. No, you don't need scalars to be integers. Scalars could be any number. You could have pi as a scalar. You could have e as a scalar if you know what those are. So any number can be a scalar. So the question was asked about my notation, my negative x and my -1 times x. So these are not unrelated. They're the same thing. If I'm defining what negative x means, and I'm saying that negative x is -1 times x. I used this := sign, which again, that's my fault. I shouldn't have put that in there. But that's just a directional equal. So you're all actually probably pretty familiar with this kind of directional equality operator because you use it all the time in coding. Right? If I say x equals 1, I'm saying by definition x takes the value 1, but I'm not defining 1 to be x. If that makes sense. I'm not overwriting the value of 1. I am overwriting the value of x. So that's what I'm doing here. This -x : -1 times x is just defining the symbol -x to mean -1 times x. I hope that's clear. And then the second, the equation number 4, which is numbered, these are all equal. These are all equal, right? So if I add x and -x, it's the same as subtracting x from x, if that makes sense. Because again, as you can see, my kind of example here, can you all see my cursor? Actually, I should have asked. Okay, so my example here of 1 plus -1, that's equal to 1 minus 1, right? So that's the same thing here. X plus -x is equal to x minus x. And then I'm going to call the 0 vector, so the list of n zeros, it's going to be called 0 sub n, and occasionally I will mess up and just write 0. Now, if you read papers for some reason in mathematics, or you read textbooks, a lot of times the textbook will just write 0. And it's for this reason we talked about earlier. When things are similar, mathematicians give them similar names. This 0 vector acts a lot like 0 does for the numbers. And so oftentimes we just talk about 0. Negative x would only be equal to 0 if x was 0. But adding x and negative x will always give you 0. If that makes sense. I'm going to go on for now. If you still have questions about negative x, we can talk about that some after the lecture. Are there any other questions about the stuff we've talked about so far? Okay. So we're going to move on then to talk a little bit about vector products. So multiplying vectors gets weird. So we've talked about multiplying scalars and vectors, and that's pretty easy. We just multiply away. There are, however, a ton of different ways to think about multiplying vectors. And not all of them are useful. So we're really there are like 3 main ways to multiply 2 vectors. We're really going to talk about one today, and then we'll talk about the other one. We'll talk about another one next week, and then we'll talk about the third maybe sometime. And the 3 are, the first one that we're going to talk about today is the quote-unquote scalar product. It's also known as an inner product or a dot product. And we write it by either using a dot, which can get confusing, or by using this bracket notation. And that's the notation that I'm going to use, because I've already used the dot to mean a lot of other things, to mean scalar multiplication, for instance. And so while it's perfectly reasonable to use a dot, and that's why it's called a dot product sometimes, I'm going to use the brackets. Now the brackets are, I would say, the most common notation used for the scalar product in mathematics. In physics and other fields, I don't know. But in math, it's definitely inner product. No, the dot product is not multiplication by a scalar. So this is the confusing part. I'm not going to use the term dot product. I'm going to use the term scalar product because that's more correct. And that's but like in Roblox, the thing I'm talking about when I talk about the scalar product is, vector3 dot. And so yeah, what does that mean when I talk about a scalar product? We'll get to that in a bit. But the other 2 definitions of other 2 ways of multiplying vectors that we'll touch on a bit is the cross product, which is denoted by this times symbol, which is why you're not allowed to use that for something else. And the so-called entry-wise product, which is also known as the Hadamard product, but that's just because mathematicians love getting their names on things. And in particular, we like giving the wrong names to the wrong theorems. But anyway, that's an aside. So what is the scalar product? Well, it's a product between 2 vectors that outputs a scalar. So we want it to take in 2 vectors, and we want it to output a number. So we're going to have to do something that only outputs numbers. And in this case, what we'll do is, if we have 2 vectors that are the same length, we're going to multiply them entry by entry. So we'll do x1 times y1, x2 times y2, x3 times y3. And then we're going to add them all up. We're going to add them all up, and that's going to be a number, because x1 and y1, those are both numbers. x2 and y2, those are both numbers. And so we multiply them, that's still a number. When we add them, still a number. And so what we're going to get out is a number, which is why we call it the scalar product. There are 4 properties of this product that make it quite nice. The first one is that if you take the scalar product with a sum of 2 vectors, it's the same thing as adding up those 2 scalar products. The second one is that if we multiply one of the vectors by some scalar, some number, we can move it around. We can do alpha x scalar product y. And that's equal to x scalar product alpha y, which is equal to alpha times that inner product. So the kind of way of thinking about this is, right, if I multiplied every value of x by 2, then this would multiply every element in the sum by 2 as well, which would make the whole sum twice as big. Another useful property is that if you take the scalar product of a vector with itself, you're always going to get a number that's at least 0. And why is this? Well, if you take the scalar product of x with itself, then you're going to get a sum of squares. You're going to get x1 times x1 plus x2 times x2 plus x3 times x3. And this is going to be a sum of squares. And so if you take a number and square it, if it's negative, it'll become positive. And if it's positive, it'll become positive. So if you add up a bunch of positive numbers, you'll get a positive number back. So this will be what's called non-negative. And actually, it has this really interesting property where the inner product, or the scalar product between two vectors, is 0. A vector in itself is 0. I need to be clear here. If and only if that vector is 0. The only vector that you can take the scalar product with itself and get 0 is 0. And that property is one of the most important properties that this has. It's one of it's the foundation for multiple fields of mathematics. That's how important it is, but I'm getting off track. But if the vectors are different, then we can get 0, even if they're not both 0. For instance, if you take the scalar product between 1, 1 and 1, -1, then you'll get 0, because you end up getting 1 minus 1, which is 0. And if the scalar product between two vectors is 0, then we call them orthogonal. So if you've ever heard someone say that two vectors are orthogonal, it's because their scalar product is 0. You've probably done this sometime. If you've ever checked if a vector 3 dot a vector 3 is 0, you've been checking if the two vectors are orthogonal, which is to say if they are at 90-degree angles from each other. So this is actually this is the best possible way you can do to check if two vectors are at a 90-degree angle from each other. That's really useful in a bunch of things. So we're going to talk very briefly about norms today. We'll talk a lot more about them next week. But basically, this property that the scalar product of a vector with itself is positive means that we can always take the square root of it, right? Because you can't take one should not take the square root of negative numbers. And so we want to make sure that when we're taking a square root that it's not less than 0. So we can basically use the scalar product to recover the Pythagorean theorem. I know some of you may not have taken geometry, so we'll not go into that too much. But basically, we can define the, quote, length of a vector to be the square root of the scalar product of that vector with itself. We'll get into this a lot more next week, but it's very useful. And so we'll talk about the implications of that and how we can use that next week. But you can see, for instance, the quote-unquote length, which we call the norm of this line in red, is equal to 5, because 3 squared plus 4 squared is 25, and the square root of 25 is 5. Yeah, in Roblox, I think it is vector 3 dot magnitude, but mathematicians dislike the term magnitude, so we use the word norm. So if you ever hear the word norm, it means magnitude of a vector. So that actually wraps it up, because traditionally college lectures only go 10 minutes from the hour, and I'm imitating that because that's what I know. So thank you all for coming. I'll stick around for a bit longer so that people can ask questions. I'll post some problems that you guys can do probably by the end, or probably by tomorrow night. I've been very busy this weekend traveling. But yeah, thank you all for coming. If you have any questions, please stick around and ask. I think, Ethan, you can cut off the recording now so that if people want to ask questions, they won't be recorded.